So what I want to talk about today is really the culmination of a few years of thinking about kind of the integration of data manipulation, visualization, and modeling in R. How many of you have seen Hans Rosling's talks? So if you haven't, your homework for today is to go Google Hans Rosling, watch one of his presentations of data. So Hans Rosling is an absolutely fantastic presenter who talks about data that looks like this. So here on the x-axis, we've got GDP. On the y-axis, we've got life expectancy. And each of these dots is a year. So you can kind of see over time what's happening with all the countries in the world. Now, I'm not going to show you any cool animated graphics like this. I'm going to show you some really boring line graphs. And this is by no means a big data set, right? This is like 1,700 observations in total. But even when you start plotting this much data, you immediately have some problems. Like, what can you tell from this plot? Like, what are the main takeaway messages? I mean, maybe you can kind of see that generally the pattern is upward. And I should mention here, this is just one of these two variables. So we've got year on the x-axis, life expectancy on the y-axis. And then each of these lines represents one of 142 countries. So you can kind of see like there's some, it looks like the trend is generally pretty positive, but we've got some weird, maybe some lines going the opposite direction down here. And this is a really common problem, right? Even with just, a couple of thousand of data points, you can't plot them all, you can't see them all. And so it turns out that even just to do visualization, doing some modeling is really, really useful. So what we're going to work our way towards is a plot like this. Now each of these dots is a country. And what I've done is I've fit a very simple linear model to each country. I've summarized that model, the quality of that model with the R squared on the x-axis, and then the main parameter of that model, which is kind of the average yearly increase in life expectancy. So when we look at this, you can see, well, a lot of these countries, this model fits really, really well, right? The R squared's up at around 0.99. But then we've got a whole bunch of countries where this model doesn't fit so well. And what do those countries have in common? Well, they're all red, so they're all from Africa. So we'll see why shortly. Why do those countries not fit this model so well? Now I'm going to show you this idea with a very simple data set. We're just going to look at basically two variables, 1,700 observations. But the neat thing about this approach is that it scales to arbitrarily complex models. You can use it with big data because it's trivially parallelizable. And then finally, there are kind of three main ideas, three simple underlying ideas that you can apply in other situations as well. And each of those three ideas is coupled with a package. So the first thing I'm going to talk about is this idea of nested data. So this is going to appear a little crazy at first. What we're going to do is make a data frame where one of the columns of that data frame is a list of other data frames. We're going to do that using the tidyr package. Then we'll talk a little bit about functional programming, basically as an alternative to for loops. And I'll talk about kind of why, a lot of people say for loops are bad. I'll talk about why they're not really that bad, but why you should be learning some other techniques as well as for loops. And we'll be looking at that with the purrr package. And then finally, a really powerful idea, whenever you've got a model and you want to visualize it in some way, it's really, really helpful to turn that model into tidy data. And to do that, we're going to use the broom package by David Robinson. So these three ideas are going to help us understand this data set. I think they're pretty simple and they're pretty general and will hopefully help you solve other problems in R. So what is nested data? Well, we've got these 142 countries, and what I want to do is fit a linear model to each of these 142 countries. And that's going to be much easier to do if I have 142 data frames. So currently my data looks like this, right? I've got a variable for the country, a variable for the year, and a variable for the life expectancy. And each of these rows is an observation. But if I want to fit 142 linear models to this, it's going to be useful to have a different form of that data. And that's what I call a nested data frame. So we're going to make a data frame that has one column per country, and we're going to have another data frame which is a list of data frames. So for example, the first data frame in this list, that is going to be the data for Afghanistan. The second will be the data for Albania, and so on and so forth. So I'm going to call this a nested data frame, hopefully for an obvious reason, because we've got data frames inside data frames. And when I kind of first discovered this, I thought that maybe this might just be a sign of madness, putting data frames inside data frames. But I think this actually turns out to be quite a powerful and useful idea, because as well as these data frames, which we have one of per country, we're going to have lots of other things that we have one of per country. Let's take a look at the code behind this. So the data I'm showing you comes from the Gapminder package by Jenny Bryan. And I've just done a little transformation. I've created a new variable called year 1950, which is just the number of years since 1950. Can everyone read that code okay?
A little bigger would be nice.
Okay, a little bigger.
Thank you.
So what I'm going to do now is create this nested data frame with sort of a combination of some dplyr function and a tidyr function. So I'm going to take the Gapminder data, then I'm going to group it by continent and country, and then I'm going to nest it. So let's see what this looks like. So now instead of a 1700 row data frame, right, before we've got one row per observation, so one row for each country for each year, now we just have one row for each country. And if we want to get the specific data for that country, we're going to have to dive into this list. Now, if you've used R for a while, you might find that str is your kind of go-to method for understanding the structure of an object. Unfortunately, str is not super useful here, as it gives us a lot of output. So what I'm going to do instead is just drill into that data variable and then look at the first value. And so this is just a data frame that has, oops, if we look by country, the first row is Afghanistan. So this is all of the data for Afghanistan. So for each year, what's the life expectancy? And then we have a few other variables that we're not going to talk about, like the population and GDP per capita. So does that make sense? So what we've done is we've gone from this one big data frame to one data frame per country. And instead of just having that as lying around as a list, we've stored it as a column of our data frame, which makes it easy to identify because the other columns are the name of the country and the name of the continent. How many of you have seen this guy before, the pipe? Okay, so if you haven't seen it before, this operation is just the same as this. So the pipe, which is often pronounced then, so x then f of y, it just takes the thing on the left-hand side and feeds it in as the first argument on the right-hand side. So the pipe is just sort of syntactic sugar. It doesn't change what code does or what it means, but it basically makes it easier for us humans to read. So when you read pipe code, you can sort of read it as this imperative sequence of operations. Take the Gapminder data, then group it by these variables, then nest it. And behind the scenes, that's exactly the same as this code. Now, functions are great because computer scientists have studied functions for a very long time. We understand how functions work and how to program with them. But the problem is, to read these nested functions, you've got to read from inside out. And that's a little challenging to do. So all the pipe does is it rearranges the code in a way that is more optimal for humans. And I think this is really important because code is a medium of communication. It's not just a medium of communication between you and the computer, but it's a medium of communication between you and other people. And every project that you work on, you're always working on it with at least one other person, and that's future you. And you really don't want to be in a situation where future you is cursing present you because you did a terrible job of writing your code and now you've got no idea what was going on. So I've experienced this many times. I'll look at my code and it's not only like a stranger has written it, but a potentially insane stranger has written this code and I have no idea what it does. It's really, really valuable when you're writing code, even if you just think it's going to be throwaway code that you're never going to look at it again. That's always the code you end up relying on later on. Very, very important to invest time in making sure your code is easy to understand, and the pipe is a great way of doing that. Okay, so now we've got a data frame. We've got one column that gives us the name of the country. We've got another column that has a whole lot of data frames. Each one gives us the data for the individual countries. And now what we want to do is fit a linear model to each of those countries. A very, very simple linear model. I'm just going to predict life expectancy based on the number of years since 1950. So this is not necessarily a model that I believe in. I don't think this model is true, but I think this model is useful because when I fit this model and I look at what remains, I've removed any linear trend. So models don't have to be true in order to be useful. And when we're going to do this, I'm going to end up, I've got 142 countries, I've got 142 data frames, I'm going to end up with 142 models. So why not put that in a column of the data frame as well? And this all works because the definition of a data frame is it is a list of vectors that all have the same length. A list is a vector, so you can have a column that is a list, and a list can contain anything in R. So you can easily have a list of data frames or a list of linear models. This is all perfectly legitimate R code, and tidyr and dplyr just provide a little bit of infrastructure to make your life a bit easier. And I think the important thing here is that using these list columns is really useful because it keeps related things together. Right? If this is your data, this is the name of the country, and this is your model, and this is the continent, if you decide you just want to focus on one continent, say Africa, you have to subset this vector, you have to subset this vector, you have to subset this vector, you have to subset this vector. And if you forget to subset this vector, then at some point you're going to try and combine them together, and they're not going to line up. And if you're unlucky, you won't get an error message, you'll just silently do the wrong thing. So this is very much like if you've ever had the experience of working in Excel, you go to sort a table by a column, and instead all Excel does is just sort that individual column, kind of effectively randomizing your data. Right? You want to keep related things together, and you want to keep them in a data frame because then you act on them as a whole. You never have to think, oh, well, I changed the order of this vector, so I've got to remember to reorder all the others. The data frame provides the infrastructure to do that for you automatically. So to fit the models, well, first of all, I'm just going to define a little function here. It is going to take a data frame as input, and it's going to return a linear model as output. Then what I'm going to do is I'm going to say, take the data split up by country. I'm going to use mutate. That is going to add a new variable. That new variable is going to be called mod, short for model, and this is what it's going to be. So I'm going to explain the map function in a little bit more detail shortly, but the basic idea is map is going to take each element of this list, each data frame, and it's going to apply this function to it, and it's going to return a list. So this is going to transform or map a list of data frames into a list of linear models using this function as the translator. So you might wonder, well, why use this fancy map function that no one's ever heard of? Why not just use a good old-fashioned for loop? And if you've used R for any amount of time, you've probably heard someone tell you that for loops are bad and you're a bad person for using for loops. This is absolutely not true. But there are some advantages to kind of taking the next step beyond for loops and learning these techniques of functional programming, which is basically, instead of you writing the for loop every single time, you're going to use a function that does the for loop for you. So in some sense, this is all about being lazy. Instead of you doing the work, rely on the work that someone else has done. And so I'm going to try and illustrate these ideas using some cupcake recipes as motivation. So here is a cupcake recipe. This is a real cupcake recipe from the Hummingbird Bakery cookbook. How many of you know about the Hummingbird Bakery? It's a fairly famous bakery here. How many of you have made a cupcake in your lives? Okay, cool. So if you've ever made a cupcake before and you read this recipe, you'll notice it's quite explicit. right? Put the flour, sugar, baking powder, salt, and butter in a freestanding electric mixer with a paddle attachment and beat on slow speed until you get a sandy consistency and everything is combined, right? Or my favorite instruction here is continue mixing for a couple more minutes until the batter is smooth, but do not overmix, right? Worst advice ever. Don't overmix. You can kind of take that as given, right? Don't undermix it either. Don't overbake your cookies. So this is great the first time you've made cupcakes. So it's very, very explicit. It spells everything out in detail. But now imagine while you've mastered vanilla cupcakes and you want to go on to make chocolate cupcakes. So what is the difference between a vanilla cupcake and a chocolate cupcake? And if they're going to switch back and forth, you might notice, well, it's that you put cocoa in a chocolate cupcake. And so you can imagine this is like a 100-page cookbook that tells you how to make cupcakes, and every page repeats this information and changes a few small things. So this is important because now that you've mastered vanilla cupcakes and chocolate cupcakes, maybe you want to go on to invent your own cupcake recipe. It's really useful to kind of be able to easily see what are the parameters that are the same and what are the parameters that are different, but it's hard to follow because there's so much text here. So what I'm going to do is I'm going to refactor this recipe. I'm going to rewrite it as if I was rewriting a function to be easier to understand. So one unfortunate story about this cookbook, my friend in New Zealand recommended it. She said this is a really great cookbook, and then I bought it and made some cupcakes from it, and they turned out terribly. And I complained to her and I said this is a terrible cookbook. But it turns out, unfortunately, I bought the American version, which uses these ridiculous, like a scant 3/4 cup of sugar instead of reasonable weight and metric measures. So the first thing I'm going to do with this recipe is I'm going to convert it to reasonable units. The next thing I'm going to do is I'm going to rely on some domain knowledge. So I'm going to assume that you've done made some cupcakes before, or we've done some baking before, and I can reduce the recipe to this. So mix these things together until sandy, and then beat them in with the wet ingredients. Now this amusing historical anecdote is that when I was a kid growing up, I did quite a lot of baking with my mum, and her recipes always really annoyed me because they were just a list of ingredients, and they would say bake hot oven 10 minutes. And there were never any instructions. It was just assumed that you would know, based on the ingredients, what to do with it. And so at that time, that really frustrated me. So I rewrote all of these recipes with very explicit instructions about what to do. And now I'm rewriting recipes in the opposite direction. So there's one other thing we can do here that's going to make it easier to generalize. I'm going to kind of use some variables. I'm going to say just beat the dry ingredients together and then mix the wet ingredients. And now that I've done that, I can put multiple recipes on a single page. And this is useful because we can now see precisely what is the difference between a vanilla cupcake and a chocolate cupcake. And it's not that you add cocoa, right? It's that you substitute flour for cocoa. So this is useful because now if you made this cupcake and it wasn't chocolatey enough, it's kind of obvious what to do, right? You put more cocoa in instead of flour. Or if it was too chocolatey, you'd put more flour and less cocoa. And now that we've done that, well, the next kind of step is to start thinking about these recipes as data. So I can now put them in a data frame, and I can fit on even more recipes on a page. So I've now added a recipe for lemon cupcakes. So what's the difference between a lemon cupcake and a vanilla cupcake? Well, instead of adding vanilla, you add some lemon zest. Right, so this is important because if you want to go on and generalize to create new types of cupcake recipes, now you can kind of see what's the same, what's normally the same, and what's different. Well, here's another recipe, red velvet cupcakes. You can kind of see immediately that these are a little different, right? They have more flour, they have no baking powder, they have more sugar, and they have more butter. So right away, you know this is going to make a bigger mixture, but it's not going to rise as much, probably. Now, there's one sort of interesting, there's still a one egg, right? Because eggs come in integer quantities. Although, interestingly, if you really get into baking, the integer number of eggs is not really accurate enough, and it's even better to weigh out like 40 grams of egg, which I assure you is quite frustrating. So what's this got to do with programming? Well, here are a couple of for loops. And I want you to just look at them for a couple of seconds and see if you can figure out what they do. What's the same between these for loops and what's different? So these for loops, so there's 3 parts to every for loop. Your for loop should always start by allocating space for the output. So here I'm going to make a vector of doubles that's the same as one element of this vector for each column in the empty cars data set. It's the first part. You always want to do this, or your for loops are going to be terribly slow if you have to grow the output at every iteration. Then we're going to iterate. We're going to say for 1 over seek along. How many of you have heard of seek along before? So seek along, let's just quickly demonstrate that. Say we've got 1, 2, 3. You seek, oops, let's not do that. Let's call it. It just gives me a sequence of vectors. A sequence of integers the same length. So it's basically like this. So what happens if I just have 2 elements in this vector? I get the numbers 1 to 2. What happens if I have 1 element in this vector? So what should happen if I have a vector with no elements in it? I should get no integers, right? And that's what I get with seek along. I get an integer of length 0. But if I use 1 to length x, r is going to helpfully count back from 1 to 0. So normally you don't deliberately use 0 length vectors in your code, but you want to protect against accidentally using it, because that's not going to give you an informative error message. You're just going to get this weird error message somewhere later down the line that's going to have, you're going to have no idea what's caused it. So seek along is just a little protection. Okay, so we've got the output, we've got what we're looping along, and then we've got the operation, extract the ith column of empty cars, compute the mean, and then save it in the ith element of this vector. So what's the difference between this for loop and that for loop? Well, we're just computing the mean in this one and the median in that one. So the problem with for loops is that they kind of tend to emphasize the objects that you're working with. Whereas what's actually important is the action, right? This is the critical difference between these 2 for loops. But it's hard to see it because it's, it's like 5% of the total characters I typed is what's actually different. So it's hard to see what's different if there's a lot of things that stay the same. And so what I think you should do instead, or what you should learn to do over time, is use a function that wraps up that for loop. So I'm going to show you the functions from the purrr package. These have many analogs in base R, but the functions in purrr are kind of more consistent and have a few shortcuts that tend to help you out. So this code does exactly the same thing. We're going to take each element of the empty cars, we're going to apply the mean to it, and we expect that the output is going to go into a double vector. And so indeed, if we look at the code for that map double function, this is exactly what we see. We see exactly that same code we used before, but instead of using a specific function like mean or median, that's now an argument to the function. So in R, functions can take other functions as arguments, and this allows us to write not a specific for loop, but a generic for loop. Now, this is actually a somewhat of a convenient lie. The source code to map double doesn't actually look like this because for various not really important reasons, I've decided to write it in C rather than R. But basically, this is what it's doing behind the scenes. It's still doing the same thing. It creates a space for the output, iterates over each thing in the input, calls the function on it, and saves in the output, and then returns it. So there are lots of other functions, right? If we've got a function that returns doubles, you might imagine we also have a function that returns integers. We have a function for characters and for logicals. And then the most generic form of all is map, which returns a list. This is the most general because anything in R can go inside a list. Now those functions have all varied in their outputs. These functions can also vary in their inputs. So for example, map2, instead of taking a single vector x, it takes a vector of x and y, and it loops through those in parallel. Right? So it calls f with the ith value, item in x, and the ith value in y. Right? And so you can kind of imagine like map3 and map4 and so on, which don't exist because there's a more general form called pmap, short for parallel map. And if you kind of, going back to the cupcakes analogy, we start thinking about recipes as data, and now you can even think about functions as data. So here I put the list of functions I want to apply in a list, and I can use some pretty terse, purrr code to basically, for each of these functions, compute it for each element in this data frame. So we're now kind of moving up higher and higher along this tower of abstraction, and maybe you'll never get to this point, but still this idea that you can write a function that wraps up a common pattern of for loop is a really, really powerful idea. So let's get back to the Gapminder data. So this is where we started, right? We've got one line per country. And this is where we want to end up, where we have one model per country, and we've summarized that model in a couple of different ways. So the first thing we did was to nest the data using tidyr. So we go from this form where we have an observation per row to a group or a country per row. And the individual data is now stored in a list of data frames. The next thing we're going to do is fit the linear model to each country. So now you can kind of understand what this map function does. It's going to take each element of this list of data frames, and it's going to send it into this function. It's going to save the results into a list. So let's do that just to confirm I'm not lying, and this really does all work. And so if we print this out, you can see we've got a data frame with 4 columns, the continent, the country, this list of data frames, and now this list of linear models. So again, if you look at STR is going to get kind of progressively less and less helpful, unfortunately. So you'll notice takes some time to print all that. But one of the things we have yet to work with the RStudio IDE team on is to make it so you can kind of more easily explore these objects without being overwhelmed with output. But I just wanted to point out one of the first things one of the reasons we're doing this, coming back to this idea of a data frame that has list columns. Now I can say, I want all of the things to do with Africa, all of the countries in Africa, and this just carries everything along for the ride, right? I get the data and I get the model, and I don't need to think about having to subset all these pieces separately. But now that we've got this list of linear models, well, what can you actually do with a list of linear models? Not a lot. So what we're going to do instead is take these linear models and we're going to turn them into tidy data frames. And the thing that's great about tidy data frames is you already have lots and lots of tools for dealing with them. You can visualize them with ggplot2, you could manipulate them with dplyr, you could even think about modeling them if you wanted to go really crazy. So to do this, we're going to use the broom package by David Robinson. It works for a very wide variety of model functions, model objects in R. It's going to convert them to different forms of tidy data. And what sort of data can we get from a model? So here I've just pulled out the data for New Zealand. I have fit a linear model to it. What can I get out of that linear model? Well, there are basically 3 things. So I can pull out model summaries like the R squared. So model summaries tend to kind of fall into 2 camps, right? They're either a measure of model quality, like the R squared, or they're a measure of model complexity, like the degrees of freedom, or they are some attempt to compromise between complexity and quality, like the adjusted R squared, or the AIC, or the BIC. So for these, you've got one row of these per model. Then we also have data about the parameters in the model, the estimates of the parameters. And you can also imagine, I'm not showing them here, but each of those estimates have an associated standard error and a t-statistic and a p-value and so on. And then we have values where we've got one row for each row in the original data set. So these are things like the predicted values, the residuals, and so on. And the broom package gives us tools to extract each of these. So glance is going to give us the model summaries. We have one row per model. Tidy gives us the model estimate, so we have one row per estimate per model. And then finally, augment gives us the things at observation level, so we get one row per observation per model. So let's do that. Let's compute all those. And again, we're going to use model. We're going to use map, sorry. So I'm going to take each of these models and I'm going to tidy it. I'm going to take each of these models and I'm going to glance at it. I'm going to take each of these models and I'm going to augment it. And so we're going to end up with a data frame that looks like this. So now I've got a list of data frames. It's my original data, a list of linear models, a list of the model statistics, the parameter statistics, and the observation statistics. And you might wonder, well, what can you do with a list of data frames? Well, helpfully, we can do the opposite thing that we did before. So remember earlier we took this regular data frame and we nested it to get this nested data frame. Now we want to do the opposite. Now we want to go from this nested form back into the unnested, the regular form. So let's have a look at that. So I'm just going to calculate those statistics. I'm going to do one other thing, which is I'm just going to extract the R squared from the glance and just add that as a specific column. So you can see here, we can see the R squared of each column, of each model. This is just a regular column of doubles. All right, nothing special here. There's just one R squared per model. And we could do things like sort all the models based on their R squared. And we can see Brazil has a 0.998 R squared, which is pretty high indeed. Now looking at those R squareds in a table is not that useful. We can instead plot them, which that plot's not very useful either. So I'm going to zoom in. So here I've got R squared on the x-axis, the countries on the y-axis. You cannot read those labels, but that doesn't really matter because you can kind of see the main story here, right? That most of these countries, the model fits really well. We've got a bunch down here where the model is terribly bad, another bunch that are kind of progressively getting better but still pretty awful, and then maybe another break around 0.75. So I made a little Shiny app to explore those, just so you can see. So these are the countries, these are plots of the countries that had an R squared of that model between 0 and 0.25. So why did these countries not fit our linear model very well? Well, the obvious reason is that the statistical reason is that these are not straight lines, right? Something else is going on in these countries, and they tend to, unfortunately, at this level, these R squared, these are all bad things that have happened to countries, right? We have civil wars, but for most of these countries, the main thing that's had this massive effect is the HIV/AIDS epidemic. And so we could look at that other group between like 0.25 and 0.5. You see a lot more African countries. If we go between 0.5 and 0.75, no idea what's going on with Bulgaria, but a different pattern to every other country. Again, we see civil war in Cambodia, HIV and AIDS, the Iraq war, North Korea, and I don't know anything about Liberia, but I don't think there's many data points here, but something bad happened there as well. So how did we make those plots? Well, kind of the key idea is to unnest the data to get it back to a regular data frame. So if you just unnest that data column, which if you remember has our original data frames, that is basically going to give us back our original data, except that we have this additional r squared column. So remember, we've got one r squared per model. So what is going to happen when you unnest the data to have one row per observation per country? Well, there's still only one r squared per model. Each model is for your country, so that r squared is going to be constant within a country, right? It's just duplicated out to fill in that data frame. Or if we look at the glanced data, this is going to give us, remember, glance gives us the model summary. So this for each country gives us the r squared, adjusted r squared, the sigma, or the p-values, degrees of freedom, AIC, BAC, etc. Or if we unnest the tidy data, we get the coefficients from the model. Right, so each model has two coefficients. So that means each row, each country is going to get two rows here. We see the term, the intercept, and the slope, their estimates, and the other variables that didn't get printed out include the standard error, t-statistic, and p-value. Now I wanted to do a plot with intercept on the x-axis and slope on the y-axis. So this data is not quite the right form for that, but it's a data frame, so I can use, for example, the tools in the tidyr package to get it around the right way, and then I can plot it. And so this plot, again, we've got one model, 1 point for each country representing the model that we fit to that country. We've got the expected life expectancy in 1950, that's the intercept, and the average yearly improvement. Now, one thing I've done here is I have sized the points according to their r squared. And that's because you kind of want to be careful about interpreting the coefficients of models that fit very poorly. Right? The fact that this had a very poor r squared suggests that a straight line is not a good model for this data set. So there's no point trying to interpret the coefficients because they don't do a good job of explaining what's going on. But there are a few interesting things here. So there's no data up here in this triangle. What would a point in that triangle represent? That would be a country. So if you imagine a point up here, that would be a country that had a very good life expectancy in 1950 and has improved rapidly since. So this is kind of telling us, this is actually quite positive, right? This is saying the countries that were worst off by and large in 1950 have improved the most. The worst off countries are catching up to the best off countries. Although we have this, basically Africa, which is the HIV/AIDS epidemic, which is not. We could also unnest the augmented data. So remember, that gives us one row per observation per model. So we can see like the fitted values and the standard errors and their residuals and various other residual diagnostics. We can use this to to plot a sort of overall summary plot. I'll do this one first, actually. So this is, on the y-axis, the residuals from the model. The x-axis is the year. Each line is a country. And then I've fit an overall smooth curve through all these residuals. So if you saw this sort of residual plot when you're fitting a model, normally you'd think, well, something looks not so good here, right? I've got some clear nonlinearity. I probably need to go back and improve my model. Now, I'm not actually going to do that here because I don't do real data analyses. I can just stop whenever it gets too complicated. But hopefully you can see how the same ideas would apply. You could refit a new model and then proceed through these same steps. And just in this case, I could also facet that residual plot by continent. And you can see that most of that unusual pattern seems to be coming from Africa, but maybe we're also seeing a little bit in Asia as well. So even though that linear model did do a really good job of getting R-squareds of 0.99, maybe there's still something that we're missing and we could go back and create a better model. So there are three main ideas that I showed you today. So the first idea is that you can put anything in a list, and you can put a list in a data frame. So that means you can store anything in a data frame. And this idea of a list column is really powerful because it allows you to store related things together. It allows you to keep the data frame connected to the model that was used to fit it. And you can imagine there's lots of situations where this occurs. In this case, I was splitting up by country, but you get similar combinations of data and models when you're doing bootstrapping or cross-validation. This is a really useful technique for keeping related things together. My second piece of advice is I think it's really, really useful to learn a little bit about functional programming. You know, you don't have to. For loops are great, and if they solve the job, you solve the problem, that's fine. But I think there are some big advantages to learning these techniques. You can't, it's not that you can't do, that you can now do something you couldn't do before, but you should find that you can do things with much greater ease. It's easier to write a for loop. It's easier to iterate over these things. So you don't have to write all that code for the for loop. You can just call one of these functions, and you know that those functions are well tested and used by lots of people. So it's unlikely that there's going to be an error. The error of you accidentally creating the chances of you accidentally making a mistake in your own for loop is much higher. Then finally, if you want to understand what's going on with your models, a really powerful technique is to turn them into tidy datasets, because you have lots of tools for working with tidy datasets, and the best way to do that, in my opinion, is to use the Broom package by David Robinson. So I wanted to finish with just one other little thing that I've been working on recently. This is a collaborative project between me and Wes McKinney, who's the author of the Pandas project for Python. And this is a new project called Feather. The goal of Feather is to kind of solve this problem. So here I've taken this CSV file, a kind of a large CSV file that's just lying around on my hard drive, about 600 megabytes. And if I read it in using, say, read_CSV, that's going to take about 14 seconds. The goal of Feather is to provide a binary file format that can be read and written much more efficiently than CSV files. So if I write that out to disk, it's going to take about 3 seconds. Currently, Feather files are actually bigger than CSV files often, but they can be read in much more efficiently. And the other advantage of Feather files is that you can share them with people using Python, and in the near future, Julia and Go and lots of other languages. And they also retain all of the type information. So when you save out a CSV file, you lose the information like this is a date or this is a factor rather than a string. Feather preserves all that information so you can read it back in without losing that important metadata. You may have used RDS for this in the past with write RDS or save RDS and read RDS. They are similar idea. The two problems, they're quite a lot slower than Feather files, and of course they're limited to R. You can't load them in from another programming language. So I wanted to finish off just to give you kind of the names of the most important things I talked about today. Really, I think in the age of Google, the most important thing you need to know about something is its name. As soon as you know the name of something, you can Google it and find out the information you need to know. If you don't know the name of things, it's much more challenging. So I used dplyr today for working with data frames, and purrr primarily for working with lists. And then I used tidyr to convert between the regular data frame and the nested data frame, which contained a list of smaller data frames. If you have models and you want to turn them into tidy data frames, Broom is your tool of choice. If you have used plyr before, you might notice some similarities between what you have done with ldplyr and dlplyr. Or if you've used dplyr and you've done some stuff with do and rowwise, What I've talked about today is basically an alternative workflow for those solving those same problems, and I think it is by and large a much, much better workflow. If you'd like to learn more about any of these techniques, I'm currently writing a book with Garrett Grohlman called R for Data Science. The goal of that book is to kind of take you from knowing nothing about R or programming to being a reasonably well-tooled data scientist. It is a work in progress, but everything is available online. And if you have any feedback, I'd love to hear about it. Finally, if you'd like to learn more about Feather, you can go to Wes McKinney's repo, where he and I have been working. Thank you.
Thank you so much, Hadley. Fascinating stuff. I can already see how nested data frames are going to change my workflow.
Awesome.
So I'm going to be back in a minute and I'll explain who I am if you're wondering. But first of all, I just want to introduce Rob from NBN, who's one of our sponsors today, and Rob's going to host our Q&A. So we've got a couple of microphones. We'll get around to you. Just kind of have your hands up and your questions ready. It's all being filmed as well, I should have said, in case you're frantically scribbling notes. We will make the slides available and the video and the audio available as soon as we can. Okay, thanks, Rob.
I'm going to take a very quick minute to do a shameless plug here. Ourselves and Roman and the guys at the Data Lab, we host a meetup group. It's the last Thursday of every month. It's in the Data Lab's building. It's Data Science and Technology Scotland, and the purpose of the group is primarily to bring together students, academics, commercial practitioners, anybody with an interest in data science, analytics and technology within Scotland. Regularly hosting some pretty interesting people who are talking about primarily applications of data science within commerce. The last chat we had along was looking at how data science impacted upon customer experience within organisations like telecommunications companies. And in the past, with the guys there, one of the more interesting chats we had was an algorithm developer, data scientist from Netflix, explaining how the process worked. So anybody who would like to come along, last Thursday of every month, hosted at the Data Labs offices, you are more than welcome. As Robin mentioned, I work for a company called NBN Solutions. Now, we are a Glasgow-based people solutions and recruitment business. We specialise in data science. And myself, two of these handsome gentlemen over here, and another two there, we are all going to be in and around for the next half hour or so. So if you're looking for anything in the way of a little bit of market knowledge, a little bit of advice, a little bit of guidance perhaps of where careers might go beyond academia, or whether or not you're just interested in an off-the-record chat, please come forward, say hello to the guys, and we're more than happy to give you a bit of advice if that's what you're looking for. Now, these chaps are actually going to work one side of the room each and bring the microphones over so that they can be heard. Thanks.
Who has a question?
You want me to grab that up? Very good work, thank you. So in a data frame, usually each column has an enforced class. It's a double. When you are using it like this, each one is a list, and the list can contain anything. There's no consistent enforced. Are you just ignoring that, or do you have something in the wings to enforce it like a stricter structure? Or?
So let's just make this concrete. So when you have these list columns, you'll notice here that each of these things is a linear model. And there's nothing stopping you from putting something else in there. You could put a table in there in this one, you could put a data frame in this one, you could put a function in this one. And there's absolutely nothing to stop you from doing that, except your own common sense. So basically, I'm going to rely on the fact that by and large, you're going to work with these things using like a map function. And I think it's going to be fairly difficult to accidentally end up with different things in here. So that's kind of my belief currently. I think it doesn't need, I don't believe I need to worry about it. So for now, I'm not going to worry about it. And if it turns out that people really do like to do bad things, then I'll think about it. But this is in line with the philosophy of R. Like, you know, R lets you take that loaded gun and point it at your foot and pull the trigger if you want, and it's up to you to avoid doing that to yourself.
Any more questions?
Anyone at the back? Do we want to take, does someone else want to ask a question? We'll get the microphone to you in preparation. Up the back on the left, yeah.
Hi, thanks for the great talk. So a comment briefly, it strikes me that the workflow you're describing here is a really different approach to what a lot of my dear friends and colleagues in the social sciences do, where they have a data set and the first thing they want to do is fit the one big model to rule them all. Yep. Which is really challenging to break them of that notion that's the way it should be done. So I guess two questions. First, with Broom, what kinds of models does it work with well, and is it extensible at all for any other kinds of models you might fit? In terms of my own experience doing some of this functional stuff, creating data columns that are lists, I've occasionally had issues where there's some subset of the data that breaks the function I want to run, and it crashes the whole thing rather than storing some kind of null or error. And that might be something that would be worth thinking about for the future.
So I'm going to answer both of your questions with Google searches. So the first one, if you go to the Broom homepage, you can't unfortunately just Google for Broom, you have to Google for Broom and R. But you'll see this is the list of packages that it currently supports, which is quite comprehensive. And David, the maintainer, is fairly active at adding new packages. And if you do want to do it yourself, it's a fairly simple process to do so. The other challenge when you're doing these map functions, the whole thing either succeeds or the whole thing either fails, which can be frustrating. So purrr provides another function called safely. And safely works a little bit like try in base R, but safely is a little bit differently. First of all, it's an adverb. So safely takes a function as an input and returns a modified function. And what it does is it makes a function that always succeeds. And it changes the output of the function so that when the function always now returns a list of two things, the first is a list and the other is an error. So for every time you run it, either the error is empty or the result is empty. So you can kind of relatively easily work with this, and you can see this. There's some examples on this page. This is again the R for data science. Examples further on. Typically, you want to do two things when you have an error. You want to extract the results that succeeded and work with those, and then you want to find the inputs that failed, and that's the other way. These are the inputs that failed. These are the results that succeeded, and then work with those. And so purrr sort of also provides you with functions to make that as easy as possible. Another question? Did you get the mic? Yeah.
Yeah, the data frames that you're talking about, are those bog standard basic data frames, or are those the data tables that people have been talking about recently?
So these are all the answer to that is slightly neither. These are what I call tibbles. So tibbles are basically, they're like 90% regular data frames. But they're kind of data frames were invented 20 years ago. And since they were invented, we've, I think, determined that some parts of what data frames do are good and some parts of what they do are annoying and stupid. And so basically what Tibble does is just it takes the good parts and, in my opinion, makes the bad parts go away. So for example, there's a function called data underscore frame, which is a replacement for data dot frame, and it does things like it basically, the main difference is it does less. It tries to be less helpful. So for example, it does not convert your character vectors into factors for you. And then tibbles have some other behaviors around subsetting that just make them a little bit more consistent. So if you try and access a variable that does not exist, you get an error rather than a null. Or if you subset a regular data frame with a single column, you'll get a vector back. No matter how you subset a tibble, you'll always get another tibble back. So they're basically sort of a thin wrapper around data frames that make life generally easier and errors more obvious. Next question.
Hey, I was just wondering, is there any ability to do parallelization within the map functions?
There is not currently within the map functions, but there is a package called, this is still mostly a proof of concept, but this is a package called multi-dplyr, which allows you to basically take a data frame and spread it across multiple cores in your computer. And then all of the dplyr functions work in exactly the same way that you're used to, but transparently the request is spread across multiple cores. So you could use multi-dplyr, and because the workflow I showed you used mutate, you kind of get parallelization for free. At some point, I think purrr will support some parallelization built in as well. I'm just waiting for basically this distributed R project to kind of get a little further and provide a common API across not just multiple core, but cluster APIs and Spark and all that kind of stuff as well. So definitely, like, it's in the works. You can kind of play around with it a little bit with multi-dplyr now, but there'll be more in the future.
I've got a question. I used R when it was called S, so that was a while ago. I've recently started using it again and found bits of code on the web, most of which don't seem to work because I'm using a more up-to-date version. So I just wondered what your advice was for how to upgrade your things used to work before for me. But I need to kind of go to the next section, I think.
Yeah, so I think you're looking for this page. So it's called Hipster, Re-educating People Who Learned R Before It Was Cool. So this is written by Carl Broman, who also learned R a long time ago, and this is kind of his notes on what you should learn to update yourself. So I don't know, I don't think if you Google for hipster, you'll find this, but if you remember, I just Google Broman hipster, and it seems to reliably get me to this page. So obviously I like this page because it tells people to use my stuff. But.
Can I ask a quick question as well? That tibble thing that you talked about, whereabouts would one find it within one of these packages?
Oh, so tibbles were kind of originally inside of dplyr, and this tibble package is now like a separate thing. So if you use dplyr, you kind of get it for free. If you want to use this outside without dplyr, you can use the tibble package, which is available on CRAN.
Another question then. Like my colleague next door, I learned R, but it was X too, but I've learned to be done a bit more in between as well. Looking at your data that you presented, my first approach to that would be to pick a linear mixed model with country as the thing.
Right.
Would you ever think of doing that?
Absolutely. So I think, so I would argue that doing that as the first thing would be a mistake, because I think one thing that is challenging with this data set is, basically a lot of the countries, a linear model fits very well. The other countries, you need some kind of quadratic term.
You need to have different variances. You can allow that.
Yeah, so I think working your way up to a single model is a really good idea. But I mean, my approach is always like start with like the simplest possible thing and then work your way up, because it's kind of easier to diagnose problems along the way to a complicated model. Because, if you've...
That's all very well here when you've got the same number
Yeah.
of for each country. Things can go seriously wrong when you have different You're getting different bits of information.
Yeah, I agree. I just think you are better off starting, sure that might not work, and it might be absolutely necessary to have a single model to pull enough information to get reliable estimates. I just worry that people fit very complicated mixed effects models that they don't actually understand. And people, I think the other problem is you'll fit, like, you pick the model you want to fit that's really complicated and includes all the scientific things and all the interactions you believe in, and then it doesn't converge. So you're like, well, I'll just drop this variable off, and it still doesn't converge. You're like, well, I'll just drop that variable off, and now it converges and you're happy, right? So, I'm not saying you can't make mistakes with this, but I think thinking about like going in both directions is really valuable.
No, I think you're all kinds of great tools for the folks to learn how to use them.
Thanks.
Any more questions?
Got one behind you.
Hello. for data manipulation, and there are now facilities offered by dplyr, for example, and now you're offering us better outlines based on broom and so on. And who knows, in a few months' time, this thing will have moved on again. If you step back and look at R as a whole, and not just your packages, the impression is untidiness. Is there any prospect of any of your packages becoming merged into base R and replacing the things that it does better?
I mean, basically, no, there's no possibility. So one thing that I had a really interesting conversation once with John Chambers, who designed the S language, which R is based on. And I said basically the same thing to him. Like, I want to have like one right way of solving it. Like, I want a best practice. Like, if you're going to do this, there should be one right way of doing it. And to John, that idea was really unappealing. Like, he wants you to be able to solve problems using multiple different approaches. And you know, regardless of whether we're on the spectrum of like having many different ways to tackle the same problem, or always having one right way, where you fall on that spectrum personally, the reality is that R is very much on there will always be many different ways to solve a problem. And I think you just have to accept it. If you rail against that, you'll just become unhappy. So you just have to accept that R is like a language of freedom. Like, lots of people can approach problems in lots of different ways. I think, you know, there's a small danger of R kind of regressing into like mutually incomprehensible dialects. But I think there's sort of enough shared code, and that increasingly like people are doing more and more in public, that I think there's going to be like dialects, but it's going to be like Scottish and English, right? You're still going to be able to understand each other most of the time, but it's not going to go too far apart. So yeah, I mean, personally, I would like to have like a very like tidy language, but it's not going to happen.
Couple of quick questions. It looks like every generation of programmers is being taught to rediscover functional programming. It's been going on for ages. Why do you think is it so hard? And will your package make it easier?
So I think and for many domains, functional programming is not a terribly good fit. And I think, you know, often I see people sort of arguing online, like, is object-oriented programming better, or is functional programming better? And the functional programming people said, yes, it's obviously better, because every problem I've worked on, it's been better. And the object-oriented people say, well, for every problem I've worked on, it's been better. And that's completely true, because you've been working on different problems. So I think, like, for data analysis in particular, I think functional programming is like a good fit, because you're often kind of doing the same thing to many different examples. I think the other thing, that functional programming is not really the most accessible discipline in computer science. And it's taken me a long time, like, you know, this cupcake analogy has taken me a long time to get to, because it's sort of so deeply internalized into me as to why functional programming is useful. It's hard to explain to other people. And when, you know, when the benefit is so clear to you, it's hard to not sort of come across as like evangelical, like you learn functional programming and be saved, which is not generally a terribly successful conversion technique. So I don't know, I'm hopeful. Like, I think functional programming is a big part of R. The goal of purrr is to kind of take the parts that don't work so well and provide wrappers around them and give a consistent interface, and, you know, we'll see how it goes.
My second question is, I see a similarity between your frame of data frames, which is a great idea, with multi-dimensional modeling in general, cubes, etc., which have in some ways solved some of the performance and scalability issues. Do you feel that this is an analogy that makes sense, and is there some symbiosis there, or is it?
Yeah, absolutely. So I think there's lots of different ways of thinking about these types of structures. And one thing that I have found helpful is talking to kind of people in different domains and different disciplines who think about these very differently. And if you talk to physicists, these are like tensors, or are they multidimensional arrays? And so some of the art of kind of making this useful is putting into a framework that is already familiar if you've used R. And that by and large means data frames. Like certainly R does have matrices, it does have arrays or tensors, but by and large they're not terribly well supported in the language. And there's no reason that they couldn't be. I mean, someone could sit down and like build out all of those tools to make them possible, but it just hasn't happened. And whereas there are lots and lots of tools for data frames and they're very useful. I mean, sort of one thing along that line is, there's Jan de Leeuw, who's a now retired UCLA stat professor, has written this. I don't know if you've heard of APL before, but it's kind of the original programming language for manipulating high-dimensional arrays. APL basically, like people make fun of purrr for being unreadable, but like APL originally had like a special keyboard that you needed to use with it. So APL is incredibly terse, but the ideas are really well thought out. And so Jan has been kind of pulling some of these ideas and writing R functions around them. I don't know, it's just thinking in arrays it doesn't come naturally to me because I just use data frames all the time. But I think there's absolutely like an equivalent set of tools you could build around arrays, but they're just a little too foreign, I think, to most people who use R. And if you do work with arrays in R, you're almost always better off converting them to data frames, and things become much simpler.
On the theme of sort of untidyr, I got tempted by data table and started playing with that, and then started using dplyr, and now I have some code that's a mishmash of the two, and I'm getting a bit of a headache trying to figure out should I just ignore data table in your opinion, or should it? Yes.
I think basically you should ignore data table until you have like more than 10 gigabytes of data. So data frame is incredibly fast. And I kind of personally believe that has sort of sacrificed some stuff on the altar of that speed. Now, like that's my personal opinion, and some people don't agree. But I think you can kind of. So one big difference between data table and dplyr is that data table does everything basically using subsetting. So in data table, there's one function that does everything that like 15 functions do in dplyr. And I think you can kind of tell, like, are you going to prefer data table or dplyr by thinking about that? Like, some people think, like, one function that does everything that, why would you want to use, like, these 15, like, verbose, wordy functions? Like, that's so much typing. Data table is way better. And other people think, well, you've got one function that does everything. Like, how do you possibly remember how it works? And if you're that type of person, dplyr is going to be more natural. So I think there's some kind of, like, breakdown, whether it's like psychological or experiential, but some people really are very, very passionate lovers of data table, and other people are very passionate lovers of dplyr. But personally, like, the type of problems I work on do not need the speed of data table, and I just find dplyr, like, obviously it's easier for me to understand because I wrote it, but I do genuinely believe for most people it's easier to understand because it is more verbose. Like, you can read it as a sequence of operations. You've got all of these hints there that when you come back to code that you wrote 3 months ago, you've got much more to kind of remind you of what's going on. With data table, very, very concise. You can probably write code faster. If you're using it every day, you can read it very efficiently, but I personally believe that it's going to be harder to understand in the long run, and harder to communicate with other people.
Any more questions?
Okay.
Nothing else? Okay, next I think we'll have a third then.